Why doesn't a container ship just tip over when it's basically a floating skyscraper made of steel boxes? Because stability isn't about being heavy. It's about where the ship's weight sits, where the water pushes back, and how those two forces create a self-correcting lever. Think of a punching bag. You can shove it, but it swings back because its weight is low. Ships do the same trick, using hull shape and ballast. A ship floats when it displaces enough water to equal its weight. That upward push acts through a point called the center of buoyancy, the average location of the displaced water. The ship's weight acts downward through its center of gravity, basically the average location of everything heavy on board. When the ship is perfectly upright, those two forces line up. But waves don't let you stay upright. The ship rolls, even slightly, and something important happens. The underwater shape of the hull changes. More hull volume goes under on one side, less on the other, so the center of buoyancy shifts sideways toward the deeper side. Now the upward buoyant force is no longer directly under the center of gravity. That creates a turning effect, called a righting moment, that tries to rotate the ship back upright. Engineers simplify the geometry using a special point called the metacenter. You can imagine it as the pivot point that the buoyant force swings around 4 small angles of roll. The key number is metacentric height, or GM, the distance between the center of gravity and the metacenter. If the metacenter is above the center of gravity, positive GM, the ship behaves like a self-righting toy. Tip it, and it fights back. But if the center of gravity rises too high, GM shrinks. The ship becomes sluggish, then unstable. Past a limit, it doesn't want to return upright at all. So how do container ships keep GM healthy while carrying towers of boxes? 2 big tools: smart loading and ballast. Loading comes first. Heavy containers go low, lighter ones go higher. That's not just common sense, it's stability math. Every ton placed higher raises the center of gravity. Ports use stability software to plan stacks so the ship stays within safe limits for roll, bending loads, and wind. Then comes ballast, the ship's adjustable weight system. Container ships have ballast tanks along the bottom and sides. They can pump seawater in or out to shift weight down, shift it sideways, and control trim front to back. If the ship is light, say it's traveling with fewer containers, its center of gravity might be fine, but the ship can sit too high, getting pushed by wind and slapped by waves. Ballast lowers the ship into the water and increases stability and comfort. If cargo is uneven, more weight on one side, ballast can correct the list by adding water to tanks on the lighter side, bringing the ship back level. But ballast has a trap, the free surface effect. If a tank is only partly full, the water inside sloshes as the ship rolls. That moving water acts like weight shifting outward, effectively raising the ship's center of gravity and reducing GM, exactly what you don't want. That's why stability plans prefer ballast tanks either pressed full or pumped close to empty, and why internal baffles exist to calm slosh. There's also such a thing as too stable. If GM is extremely large, the ship snaps back upright fast. That can mean harsh, quick rolling, bad for crew, bad for cargo lashings, and hard on the structure. So stability isn't maximize GM. It's optimize GM for safety and motion. In real storms, the ship's safety comes down to the righting moment versus wave and wind forces. If the ship's center of gravity is low enough and ballast is managed correctly, each roll produces a restoring torque, like a built-in reset button. So the ship isn't stable because it's huge. It's stable because it's designed to make buoyancy move in a way that pushes it back upright, and because ballast and loading keep the center of gravity from climbing into danger. Next time you see a container ship, picture this: gravity pulling down through its average weight point, water pushing up through a moving support point, and the gap between them acting like a lever that straightens the ship. Now your turn. What should we explain next? Why ships don't sink when they get holes, or how anchors actually hold in soft seabeds?